Okay, so I'm here to talk about the 8-bit register that we built for the ECE 140 VLSI design course. This was built by myself, Matt, and the team members Pappu and Joe. And what I want to talk about is the objective. The first thing we wanted to do was build an 8-bit register that was able to count the high and low bits. And this is useful so the CPU can read the outputs and know exactly how many high bits or low bits are in that register. This allows for calculating the power consumption of that register and many other applications. So the first thing I want to talk about here is our full schematic. This includes a bit comparator or a counter that counts the number of high bits that are in our 8-bit register. At that point, a 6-bit output is fed into a cascaded ripple carry adder, which outputs a 4-bit BCD output, which can count obviously up to the 8 bits that are within the register. The next thing I want to talk about is our 2-bit adder. This is cascaded 3 times, so we have 3 of these full adders. How these work is there are 2 inputs along with a carry in. So as 2 bits are fed into the first adder, a carry out comes from the first adder. That carry in is added in to this schematic, at which point we have a 2-bit output. One is the output and the other is the next carry out. So if I look at the truth table, I can explain a little better. So if we have 2 bits, 2 zeros, and we add a carry in of 1, our output is going to be a 1. And this occurs by 2 XOR gates, 2 AND gates, and an OR gate. So as an example, if I were to have all 1s as my input in the register, we would have all 1s on our A, B input, and our C in would be 0, at which point we would get a 1, 0 on the first full adder, which represents a 2. If that's added 3 times, we get the 8.
Okay, myself, Pappu, Kumar, Yadav, I have come here to explain regarding the layout part of our project. What basically we are doing over here, this is the complete layout version of the entire project, and it consists of all the elements, segments represented by the schematic image part of the project. So basically what we are doing over here, it contains like 4 of the XOR gates and 4 of the AND gates and 1 OR gates. So we just, in order to explain that the entire layout, we bring one of the XOR gate and try to explain the layout part of the XOR gate. Here we can see the pink color that represents the input parts, like A and B coming as the input, and this comes as the output. The blue line, you can see it comes as the output. And my teammate Matt has already explained how the XOR gate works with his truth table. And here we can see as the entire layout, it looks pretty complicated though, but still it's not as complicated as it looks like. We can see like all of the 8 bits inputs coming over here from the register, and we get like 4 outputs as in terms of S0, S1, S2, S3. And S0, S1, S2, S3 represents the BCD coded like output of these counted values of highs and lows. And further after this, my teammate Joseph will be explaining the project.
Hi, yes. As my teammate Pappu, he just explained the layout version. My name is Joseph Kaye. I'm going to go over the simulations for some of the cases we did and also the errors that we were able to get. The first case we did, as you can look right above in figure 7, is our test case number 1. For this case, we're displaying one high signal that is in the 8-bit register, which with that one high signal, our outputs would be in BCD, which will show in a decimal form of 0001. We also had a second test case, as you can see right here, number 2, as we're displaying 4 high signals, and it's also in an 8-bit register, and we display that in BCD, and our 0100 is the 4 decimals it represents. Right here, we're able to see the delay before we get the high output, and this red segment is a little bit of error that we got. Now, what I want to show you is the last test case that we did where we're displaying 0 high signals, and it's also in an 8-bit register, and of course when you display zeros, your BCD is all zeros. So we got 4 zeros to represent zeros in the decimal form. and you're able to see the delays. Right here on this chart that we did on Excel. Okay, so this just showed all of our test cases and the error results, and now Pappu will wrap everything up.
I'm back. Just wanted to conclude this entire project out here. So this is how we just completed this design of 8-bit register counter. We just like the output value represents the count of the number of ones and zeros in terms of BCD binary coded decimal digits. And here, this is how we just concluded. Thank you.